So there's a slide on this titled Depth Variation, where we just have exactly the same formulation from the U-nauts on the right. Okay, so that gives us that's our part A, and we're just evaluating the same for the base of the turbine. Is that right? Happy with that? Waves are obviously somewhat more unpleasant, but we are having no tide.
I'm going to bin out of this.
Yeah. So you can see where it's going down again. So depth profile, I don't know, you work through the numbers for that. It's not massively awkward. As long as that value is bigger than that value, you're doing the right thing, basically. So yeah, so that comes out as 0.96 times 3 delta. So pretty close to the surface velocity. But the point is we then have the top of the blade being subjected to a different flow speed to the base. So if we just run through base one, the base 22 metres. So 0.89 base. So this value is 0.96 naught, and this value is 0.9 naught. Alright, so that's part A. Yep.
The UZ, is that the velocity difference, or do we need to take different Z values to find out the velocity difference?
No, UZ is the actual velocity at each value of Z. So use function Z. So there's a difference then is whatever, that one minus that one. So it's 0.07 of U naught.
So why is it 0.07?
Because 0.96 minus 0.89 is 0.07. If we want a difference. Yeah. So these are the actual values of velocity in meters per second as a function of depth. So if we want a difference between 2 points, we either need to take a derivative, which we don't really want to do, or you need to take the difference between two to calculate values. Okay, so that's in the absence of any waves, and then the other part says what the waves do for a given period and a given depth. Not much information. We've covered this in more detail in previous years, so I'm not that bothered about you looking at this in much detail, but we've got the same configuration. We've got the surface down here, but now we've got waves over our surface. And we've got our turbine geometry in the same location. So we're interested in a point. We're interested in a point that's at Z equals minus 12 and minus 28. And a second point at Z is equal to minus 28. Right, so beneath surface, we know that there's a pressure variation, and that pressure variation, so from the waves part, we know there's a pressure variation, and we know that a pressure variation drives a velocity fluctuation. So this is just picking out two equations from the notes and solving accordingly, really. So we can get a description for particle velocities in a fairly long-winded expression in the form of Ux is equal to, and these are given on influence of wave slide in intro, right, tides intro. Right, so we've got ux is h over 2, right, times gk over omega. This equation would be given if needed, so fret not as you're reading through. Cosh kz plus d over cosh kd. Right. Right, and then there'll be a sine or a cos varying term on the right. Okay, so what this tells us, so this has got cos over on the right side, but let's ignore the cos bit because we're interested in the maximum. Velocities and maximums occur when the cos bit is 1. Okay, so we just want to evaluate this expression and go through and plug in the values that we know. So the problem is, at the moment, we don't really know anything about what the wave condition is doing. We know h. Has everyone got the value of h?
1.4. 1.4.
1.4 meters. Right, so h, or those who h is the height of an individual wave cycle, and in a regular wave, not irregular, regular beginning with r, wave, that means it's the height of, well, the elevation of the maximum, that point, minus the elevation of the minimum. So that is height, right, and that is 2 times the amplitude as a point. Right, so bear that in mind, there's various ways of getting that backwards. So that's applicable for a regular wave, and that's what's meant by that h. So we've got h over 2, just so that we don't have just amplitude, basically. Okay, g, we know that's fine. D, we know that's 50, and Z, we know we want 12 and 28. So the difficult ones then are omega and k. Right, so k is wave number. Right. Which is for a given water depth, well, for any water depth rather, let's start with that, is given as 2 pi over a wavelength. Right, so that's an arbitrary known. K is related to L in the same way as omega is related to T. Right, so it's a spatial equivalent of an angular frequency. Wave number equals 2 pi over L. So for this case, and this is a particularly awkward one because it's shallow water, we need to solve another slightly awkward equation to get to K in the first place. For pretty much everything that you're interested in, we're going to see in deep water. So for our wave energy devices, we've got an approximation that L is gt squared over 2 pi. Right, so that's okay in deep water. So that's alright for pretty much all of the wave part. And we've used that a few times to get maximum power output from a point absorber, for example. Right, so we could make an estimate of the wave number in this case using that formula. And that we're only after an estimate of the maximum velocity, so that would be an OK starting point. Right, so we could use that. We've got 8 seconds for our wave period, so that would give us 64 which is 6.28, so that's about 10 times 10, so that's about 100 metres for an 8 second wave. Right? And so that approach would be absolutely fine for this part. Strictly for any water depth, well, let's put it up here because the power's up here comes first, we would have to solve omega squared is equal to gk tan h k d. Right, which again, for the purpose of this course, is just a given formula, and for the purposes of civils was slightly more convoluted. Alright, so you could evaluate that to get k, because we know omega. Omega is related to t by the usual way. Omega is equal to 2 pi over t. T is equal to 8 seconds in this case. Right, so you could evaluate either. Really, that's going to be pretty close to that in this case. Doesn't really matter too much. Just get to a value of k. Right, so let's take this one as a approximation. Well, I suppose we should say here revision formula. So 2 things on this. One, this is a hyperbolic function, so it's not tan times h. it's all one function in your calculator, right? In case you're not familiar with it from other sources. So that's just height tan, hyperbolic tan, right? K and D is our depth. Okay, so we typically solve this by iteration because it's the most straightforward way. So you just write K is equal to omega squared divided by G tan H KB. Guess that and keep iterating until completion. I plus 1. Right, and that's K. Right, so just solve via that route. But it doesn't really matter for the purpose of this. So if we take this as a starting point, just to give us an estimate, which is what we're interested in, we've got 2 pi over a wavelength of about 100. Right, so that means that the distance from one crest to the subsequent crest is about 100 metres, or say L, approximately 100 metres, and T is equal to 8 seconds. Right? So it takes 8 seconds for that wave crest to get to there. Okay, so once we've got that, and so let's say then L is then about 100, so 2 pi over 100 equals 2 pi over 100 equals 6.28 over 100, 0.063, let's call it. Because it's slightly more than 100. Right.
Excuse me.
Yep.
Where did you get the 100 from?
So 8 second. Oh, this was a very approximate calculation. 8 second wave period. So 64 for here divided by 2 pi. So that's about 10, and then times by gravity, which is about 10. So correct me if you want a more accurate value, but that seems
99.9.
Right. So it's just from that one. But as I say, you could evaluate that, so feel free to do so, but I suspect it won't differ massively in the process. Okay, so once we know those things, we can plug into this formula. So now we're back to the situation as with this, just substituting values. Alright, so we've got a 1.4 metre wave height, we've got gravity we know, we've got K of 0.0628 prox, and we've got K here, etc. So we just evaluate for our 2 depths. And what we should see, again, is that we've got particles at this depth, which are doing something like this, and particles at this depth, which are doing something slightly less. Okay, so if we take our couple of points of interest here, so we can go sideways, we've then got, we can see what happens at the surface. So if we were at this point, at z is equal to 0, all of this bit's going to cancel out because we're going to have just cos kd over cos kd. So all that's going to go to 1. All that's going to cancel out. So if we want ux as a function of z, then we're just evaluating this. So if we do z is equal to 0, to start with, we would have just h over 2 gk over omega. And that is getting rather miniature. Replace. Right, so that's the value at mean waterline. So we can work that out accordingly. So as we go down through the water column, we're then just multiplying that value by, so that's that first constant, by our depth decay term. So then we can evaluate this whole hyperbolic bit separately. So then everyone gives a number for that. Let's put it as another line. Gets to, so that's 0.7 times 9.81 times 0.0628-ish, divided by omega, which is 2 pi on 8. Right. Is that legible? Possibly not.
No. So I'm getting that as 0.55 metres per second. Anyone get that?
Yep.
Yes.
Yep.
Metres per second. Right, so then what's the next step down? We just add our depth decay term. So if we go then to z is equal to, what do we say, minus 12 metres. Minus 12. We've got that value. Times our depth decay term. So we've got 0.55 because the constant out front is the same, times cosh of k, which is 0.0628 approximately, times z plus d. And that's the same as down here. Z plus d, so minus 12 plus 50 gives us our 38. 38 divided by cosh of the same 0.0628 times 50. Okay, and plus some flute, that actually comes out as the same value, I think. Like 4 minus 0.47. Okay. Equals our velocity again times okay, so that's just substituting values into that expression. Well, just substituting values into there. So that approach isn't really that important for tides, but this depth decay thing is exactly the same for our pressure calculations. Okay, so obtaining K and using for pressure calculations would be exactly the same. Right, so the key thing is that Z is negative from the free surface. And so all of that depth decay term just reduces to 1 when we're at Z is equal to 0. Okay, so for the top of the turbine then we have, whatever that is, 0.55 times 0.47, it's about 0.52 or something. 4.26. Okay, so at the surface, then we've got a velocity that is fluctuating. So at this point, let's draw it off to the right a bit. At this point, we've got particle velocities that are 0.55 to minus 0.55 around the mean position. And then at this point, we've got particle velocities that are, whatever we just calculated, 0.26, 0.26, and minus 0.26. So this one is occurring when we're underneath the wave crest, when we're got our cos term as 1, and this one is occurring when we're underneath the wave trough, when our cos term is minus 1. So our velocity is fluctuating by double that amount onto our tidal turbine. Right, sorry?
Could you lower that board a little bit?
Sorry?
Can you lower that board a little bit?
Alright. Particle size distributions. Slightly attentive, yeah? Or SPH. People over here read any of that? See what's going on over there? So here, the next step, I guess, over here. So if we have z is equal then to minus 28 meters, then we have u x equals 0.55 times cosh of 22 times 0.068 divided by right, so it's saying I think that's 0.55 times 0.18. Alright? Ish. Anyone not getting those numbers? So we wouldn't expect to remember those, that equation or that equation, they're pretty awkward. Probably that, as that's fairly fundamental to the wave part of the course, but let's take the time. And it's only really a one parameter. So does that actually answer the question? So again, that's velocity difference. So as you were saying before, so it's just that minus that. This is giving us the same as that expression. It's giving us the depth profile of velocity rather than the difference between a given point and another point. So our actual du then du is equal to 0.16 meters per second in that case. The time variation is much bigger than the spatial variation in that instance. So that would be our really need all the other bits in terms of the surface. All right. That's not big.
Could you please do question 4 from Wave tutorial?
Ah, yes. So I see forewarned, it's probably about the worst question. I don't know. So what is the question actually asking is my first question to you. If we can understand what the question is asking, we can get quite a long way. What's the configuration of our system if we look at it from the side? So start with our free surface and some waves, and then put a body in those waves. What do we want to know? What's the geometry of the problem? That's the general question. So can anyone explain in words, different to mine preferably, what this system looks like? We don't know the water depth, so it's deep water. Right, so what we've got is a free surface. We're going to be able to see this one. Let's start with a free surface. Right, that free surface has waves oscillating about it. So that's our z is equal to 0. Right. So we've then got a device of some description which sits in the water and looks something like that. Okay, so dimensions are 4 metres by 6 metres. 6 metres up and down. 6 metres up and down. So in, let's draw some scales somewhere here. So in that direction is 6 metres. In this direction, that's the middle then, it's 4 metres. Let's go across there. Right, 4 metres. And in that direction is, what did I say, 10 metres. 10 metres. Okay, so you put that's just a 3D direction now, but we don't need any other information in that plane, so let's not sketch anything over there. Right, so that's our boundary. That's the outer surface of our geometry sitting in presently undisturbed water. Okay, so we want to know the horizontal force, or the amplitude of the horizontal force on that structure. So we haven't really looked at that in detail, but it's the same as getting the vertical force in many ways. So first off, how would we get the vertical force on that structure? How would we get the Frau Krumov vertical force on that structure? What is Frau Krumov? Some of you do know that. I know that some of you know that because I've talked about it. So, we've got some more axes over here. We can have a pressure distribution through this wave field vertically. Right, we've seen that velocities decay vertically, and pressures also decay vertically because they follow this depth decay function like this, although they have a different constant out front. Right? So we could look through our notes and we could find an equation for the depth variation of pressure. And it's quite a long equation because it's got 2 parts. So we'll write that, so we're going to come back to it. So we could write Pz n is equal to something. Anyone got notes to obtain that? Should be in the solutions to these sheets.
Mean tutorial solutions question. Do we need to know that equation?
Sorry?
Do we need to know the equation by heart?
No. It's 15, isn't it? Wouldn't worry about that. No, but it might be presented in 2 parts. So we might have minus rho gz, which is what we have in the notes, plus, what is the rest of it? Minus 6, constant. Just